So when we're looking at electric field lines, um, the field lines we saw could tell us how intense the field was, because where we saw a lot of field lines together, there would be a lot of field. And if we didn't see any field lines, we knew there was very little or no field. Now, mathematically, we're going to get into an equation with electric field because y'all knew that was coming. So the equation for the electric field is simply, by definition, the electric field is equal to the electric force divided by the test charge. Now, on the equation sheet, you're going to see this as a magnitude because we just talked about how you determine the direction of the electric field. It's all based on what type of charge is creating that field. So, just a reminder, if you're trying to fill in all the blanks, that the E stands for electric field. Its units are going to be newtons per coulomb, because the numerator is the electric force on a charge, and its units are newtons, as all forces are. And Q naught is what we call the test charge, or the charge creating the field, experiencing the field. That might be a helpful word to have in there as well. All charges are measured in coulombs. So let's look at an example problem. A proton is placed at a location where the electric field has a field strength of 10 newtons per coulomb to the left. What is the force, magnitude, and direction on the proton? Okay. We're going to do this by having both a magnitude area as well as a direction area. Since what we're practicing right now is the equation, let's start with the magnitude. Okay, so when we start with the magnitude, we can say that the electric field strength is equal to the electric force acting on the charge divided by the small charge experiencing the field. Okay, so in this case, our electric field has a strength of 10 newtons per coulomb, and our charge is a proton. So E would be E times Q naught, I should say, would equal the electric force. I'm being a little bit lazy with my my absolute values because I'm only going to be plugging in positive values anyway. So that means I've got 10 times the charge of a proton, which is 1.602 times 10 to the negative 19th. And you can find that on the back of your equation sheet, which would be the electric force. And since all I have to do is multiply by 10, that just changes the exponent. So that would be 1.602 times 10 to the negative 18th newtons, the force of every electric, the units of every force. So we're all set there. Now for the direction. We're told that the field is going to the left. So let's start by drawing a field to the left. And I'm going to be just a little bit over the top on this just for, being me. And inside that field, we're going to put a small positive charge. Now, the field is created by some unknown charge arrangement. Now, that is actually really important to understand because if we knew how the charges were arranged, we could easily do the attracting and repelling, but we don't have that pre-described for us. So we have to think about it ourselves. So my favorite way of doing this is to imagine charge clouds. And this sounds silly, but I swear it worked for me. And I think it can work for you. So what I did is kind of imagined if there was a cloud on either side of the field, okay, and that cloud was charged. Well, from our previous knowledge, we know that electric fields move away from a positive charge and toward a negative charge. So now all I did was add in those charges in my imaginary clouds. And now it's pretty safe and easy to see that this proton here is going to be repelled by the positive charge cloud on my left, on my right, and will be attracted to the negative charge cloud on the left. So it experiences a force to the left.